Hi, so today we will learn about how to add a new hardware in existing Android device. So this is a so we will study about this today. So adding support for new hardware. There are cases where your embedded system includes hardware that is not already supported in Android, and while some of work you can do inside ASP is modular. Adding support for new type of hardware is trickier since it requires knowledge of some of Android internals. This appendix shows you how to extend Android various layers to support your own type of hardware. While you may not be interested in actually doing support for new type of hardware in your system, you might find this appendix instructive if you are trying to understand the intricate details of how the various layer of Android stack actually come together. Also, while this appendix demonstrates the modification using 2.3 Gingerbit code base, the mechanism and Java code being modified are very similar in 4.2 Jelly Bean, where major differences exist. They will be pointed out in the text. The basics, as we discussed in chapter 2, contrary to understand vanilla Linux, Android requires more than just proper drivers to function on the hardware. What is trying to say? Android requires more than just proper device driver to function on hardware compared to vanilla Linux. It in fact defined a new hardware abstraction layer, HAL, which defines an API for each type of hardware supported by Android core. In order for a hardware component to properly interface with Android, it must have a corresponding hardware module unrelated to kernel modules that confirms API specific for that type of hardware. Generally, each type of hardware supported by Android has a corresponding system service and HL definition. So there is a light service and a light HL definition. There is a Wi-Fi service and Wi-Fi HAL definition. Okay. The same goes for power management, location, sensor, etc. In below figure illustrate the overall architecture of the Android hardware support. Most of these system services, of course, typically running with the system server, as we discussed earlier. There are two general categories of HAL modules, those loaded explicitly through a runtime call to DLOpen, and those automatically loaded by dynamic linker, since they are linked into libhardware_legacy.so shared library. The API for former in hardware the APIs for former are in hardware /libhardware/include hardware, and the APIs for latter are in hardware / live hardware legacy include hardware legacy. The trend seems to be that Android is moving away from legacy. The interface between those .so file and the actual drivers through /dev entries or otherwise is up to manufacturer to specify. Android does not care about that. It cares only about finding the appropriate HL.so modules. One of the questions I often got is, how do I add support for my open type of hardware in Android? To illustrate that, I have created an OpenSys HAL hardware type and have posted the code that implements the HL type of on GitHub along with very basic circular buffer driver. If you copy the content of the OpenSys HAL hardware project over an existing 2.3.7 R1 release of open Android open source project and build it for the emulator, you should get yourself an image that comes up with the OpenSys service. The latter relies on the circular buffer to implement a very basic new hardware type. Obviously, this is but a skeleton to give you an idea of what it takes to support for a new hardware type. Your hardware is likely going to have completely different interface. So now come to the what is the system service. So system service, to illustrate how a new system service is implemented, I first added a OpenSys service.java in framework based service Java COM Android service, right? Okay. So what he has done, he has made one .java program in this location, framework based service Java COM Android server. Now this file implements the OpenSys service class, which provide two very basic call to outside world. Public string read, public service read.
26 को ही आएंगे या तो 26 को ही आप कर दीजिए जो भी मतलब है। हाँ, सुबह ही आ जाएंगे। वैसा करती हूँ मैं थोड़ा बहुत साफ सफाई। हाँ, यहाँ थोड़ा कर दीजिए ना, 26 को पानी डाल दीजिए। हाँ। उठो।
So this is the Java code. Public string read. This is the read function, and this is the write function in Java. Right? If you follow what he is saying now, if you follow the code for the new type of hardware, you will see how I added and implemented corresponding to each of these. Each of these calls at every layer of Android. So for example, if you look the system service, if you look at the system service read function, this one, it it does something like it does something like this. Read, suppose some one argument as max length is given, an integer length, and then this is a array name is byte, okay, and copying into the another array. So one function read underscore native passing one native pointer buffer, then calling to string buffer something, I don't know. This doesn't looks like a C program, so maybe it's a Java program. The most important part here is being the call to read underscore native, which is itself declares declared as follows in the operating service class: private, static, native, int. It's a totally, I think it's a Java code. Read native, passing one integer and one array. By declaring the method as native, we instruct the compiler not to look for method in any Java code. Instead, it will be provided to Dalvik virtual machine as runtime through JNI. And indeed, if you look at this location, frameworks, BA service, JNI directory, you will notice that an android.mk and onload.cpp have been modified to make into account a new com underscore android underscore server opacity service.cpp. The latter has a registered android oper service function, which is called at the loading of live android server.so, which itself generated by android.mk. I just mentioned that android.mk. So then that registration function tells Dalvik about the native method implemented in com android server operations.cpp file for the operating service class and how they can be called. Okay, so this is an array. So what is this, how it is and how it is? It's a type, it's a method table, and which is type of JNI native methods. So I think these are the function names: init native, finalize native, read native, write native, test native, and those another values are I think this is the function pointers for those functions. And I do not know what does mean by IV. Okay, we'll see. And another function is the register android server operating service, and it's passing JNI environment variable pointer for this. Okay, this environment pointer. Now it's register. Now the function is JNI register native service method, and so passing this environment and this path com android server operating service, and passing this method table. Which method table? This method table, and any lem, and also is passing method table. Really, I'm not understanding what it's trying to say. Okay, so the above structure contains 3 fields per method. 3 fields per method. Which structure? 3 fields per method. The first field is the name of the. Okay, this is 3. This is structure. Okay, which structure? GNI native method. It's an structure. So first field is the first field is the name of the method. Okay, fine, it's look like a method name, and method is defined in the Java class, okay, while the last field is corresponding to C implementation in the present file. Okay, so this is the Java function, and this is the corresponding C function. Okay, this is like a interface. So how Java code will interact with C code. So this is the GNI implementation, Java native interface. Okay, got it. So what is saying in this case the names match as they do in most cases in Android, but that does not have to be the case. The middle parameter might seem a little bit more mysterious. Confusing. It looks like confusing. The content of parentheses are parameter passed from Java. Okay, passed from Java, and the letter on right of parenthesis is the return value. Okay, so what it's trying to say, the content of the parenthesis are parameter. The contents of parenthesis are the parameter passed from Java, and the letter on the right of the parenthesis is the return value. Right is the return value. Okay, init underscore native function, for instance, take no parameters. Okay, this is inside a value, that means if this function takes no parameter in Java. Okay, no parameter, and returns an integer, I for integer. This is a return value, and inside the braces if it is written anything, so it's taking no argument, but returning an integer, I for integer, and returns an integer. While read underscore native, this is Java function, and this is C function, taking an integer, has 2 parameters. An integer, it looks like I here, an integer, and a byte array. Okay, this is called an array. This is a sign of array. This one, one integer and byte, one byte array, and a byte array. So byte array, and returns an integer. Okay, got it. Okay, now come to the, as you start playing around with Android internals, you will often have to deal with GNIsm such as these. I recommend you take a look at Java Native Interface Programmer's Guide and Specification by Sang Liang for more information on the use of GNI. And there is implementation of read underscore native, and there is implementation of read underscore GNI. And here is implementation of read underscore native. So read underscore native, this is a GNI environment, GNI env structure pointer, and G object, and one integer, and one byte array buffer, something they are passing here, and it looks like a C function. Name is exactly same as in Java and here. Okay, so overseas this one device, this one PTR, there's nothing else, I think. So value assigning to the div, then defining real byte array length, then environment, this function, this variables is a structure pointer pointing to an get byte array element function, which in which we are passing in one buffer, this buffer, and passing second parameter as null, and returning an byte array, some real byte array, something. If not null, div is not null. If it is not null, if equal to null, return 0. Okay, if it is, then div read, this read function, we are passing real div byte array, and one function get array length buffer, this one, to read. Okay. This is C function, C implementation for read underscore native. Okay. First notice that there are two more parameters than in JNI declaration above. All JNI call start with same two parameters. A handle to VM virtual machine making the call, environment, and this object corresponding to the class making to C class. Okay, so this is constant for all thing, right? Also notice that the byte array is not used as is. Instead, environment get byte array element and environment release byte array element are used at the beginning and the end to obtain and later release a C array that can be used by the present C code. Instead, don't forget that JNI calls are carrying Java type objects into the C world. What? Don't forget that JNI calls are carrying Java type objects into the C world, while something such as integer can be used as it is. Okay. Other objects such as array need to be converted before and after use. Now while some things, okay, this is done. Now most importantly operative part of read native is the call to dev read. But what does this function pointer lead to? To understand this part, you need to look at native underscore init underscore native. Okay, so this is the init underscore native. This is again a C function. Okay, so operation hardware module ID. Okay, and returning GNIT something return. Then two important things are happening in this function. First, the call to hardware underscore SW underscore get underscore module function, which requests that HL load the module that implements support for the overseas hardware module ID type of the hardware. Second, there is the call to loaded module open function. This will take we will take a look at both of these below, but for the moment note that the former will result is an .so being loaded into the system service address space, and the latter will result in hardware specific function implemented in that library functions, such as read and write, being callable from com underscore android underscore server underscore cpp file, which is essentially the C side of new system service we are adding. Okay, now we are coming to the HAL and its extension. The HAL, which is in the HAL is under which is in hardware slash provides the HW underscore get underscore module all above, and if you follow the code, you will see that hardware get module ends up calling classic TL open, which enables us to load a shared library into a process address space. Okay, then if you want to understand about DL open, just go to the main DL open in Linux. The HL won't, however, just load any shared library. When you request a given hardware type, it will look in system lib hardware for a file name that matches that given hardware type and the device is running on. So for instance, in case of the present new hardware type of hardware, it will look for overseas sw.goldfish.so. Okay, Goldfish is being the code name for the emulator. Got it? The actual name of the device used for middle part of solution for this. The actual name of the device used for the middle part of the file name is retrieved from one of the following global properties: ro.hardware, read only product board, ro port platform, or ro.arc. Also, the shared library must have a struct that provides HCL information and that called Hall Module Info System str. Okay, we will see an example next. For example, the definition for this new hardware types itself is just another header file. In this case, upsys.h along with the other hardware for definition. In hardware, live hardware, include hardware. If not define Android upsys.interface.h, define this. Okay. Include stdin cdef typed this one include hardware.h. You can declaration something. Upsys hardware difference module ID is upsys. Okay, the module ID is nothing but upsys hardware. Okay, now structure, defining one structure upsys system device, one again structure hardware device common, and then function pointers, one function pointer, two function pointer, third read, write and test. Okay, and declaration. In addition to the prototype definition for read and write, note that this is where upsys hardware module ID is defined. The latter serves as the basic for file name looked for on the file system that contains the actual hardware module implementation. So now HCL module. What is HCL module? The theory is that each device will require a different HAL module to support a given hardware type. For Android phones from separate vendors, for instance, will likely use different graphic chips and therefore likely to have different GR alloc modules, graphic allocation module. I think typically the HAL module are added to ESOP sources in lib directory within device vendor product. In the case of emulator, however, the virtual devices is devices it supports are in SDK_emulator. So this is where the goal-based implementation for our type of hardware is added. The device vendor product. The upsys hardware type is not really fancy, and therefore the implementation for Goldfish fits in single file. Upsys hardware QMA.c in order for the library resulting from the build of this file to be recognized as a HCL module. It ends with the snippet. Okay, hardware module type. Okay, so structure is nothing but a hardware module method, and variable name is upsys this one. This is open, so this is a function, this is open function, and another is hardware module info sim. So module tag, hardware module tag is this one, major version number, minor version number, then the ID of this hardware. Okay, name is upsys hardware module, author upsys corporation, and method is the address of upsys module method. Okay. Note the presence of the structure called HAL module system. Furthermore, note the upsys module method and open function pointer it contains. This is a very same open called by init native. Earlier ones the HL module is loaded, and here is what the corresponding overseas hardware does. Overseas, open overseas. So what does it do? It's calling a malloc function. It's calling a malloc inside of the function. Then I'd have a tag, this one, then Dave. Okay. So what are the parameters? One structure pointer, one string, and hardware device address for the device. Okay. And the Dave will copy to the device. Which Dave? Where we got the Dave? Okay, we have defined here. We have declared here this table. So Dave will call the malloc, and we will get the address. You will get the memory address here, and we will fill this Dave structure. Tag, we will copy the tag, version, module, read, write function, and test function. Then this Dave will copy to this device function. Okay. Then FD. Now we will call the open. Open is open the device file. We are opening device file. Circular char, read, write. Okay. D opus hardware has been initialized. Fine, that's fine. So this is the open function. Now the function main purpose is to initialize the Dave structure, which is opus Dave device. Sorry, opus device underscore T type. The same type defined by opus.h, and open the corresponding device in /Dave, thereby connecting to the underlying device driver loaded into the kernel. Probably some device driver might require some initialization here, but our purpose is this is sufficient. But for our purpose, this is sufficient. Finally, here is what opus underscore read does. So read from the opus read function is this one opus hardware length read function, or not whatever the FD, pass the FD, read from read and read from this FD, and read from this FD and keep it here in this buffer and up to this length. Okay, fine. We are not doing too much error checking here, but you should in your case. Okay, we will do. For instance, we are not even checking that the call to open the device driver succeeded. We usually should. Yeah, we do actually. Still, the call path should be clear. The system service says read call results in JNI call to read underscore native, which by the way the HAL result in call to the HAL module opus read. Existing system services and HAL corresponds have similar type of call path. Most however have a much larger number of calls defined in their system services, and therefore a lot more happening in between the various layers involved in providing support for their specific type of hardware. Calling the system service. Okay, this we will see later. We will stop here.